morning, everybody. So my presentation today is a sketch of a program on how to introduce machine learning techniques in reduced density matrix functional theory. So the main topic is how to produce in general universal functionals, not only in RDMFT, but also in DFT. So the initial inspiration was the previous work that we did in developing functionals for properly DFT. And then I will tell you what we did for RDMFT. So I would like to start with this provocative slide. Is that what I have learned these days here in this workshop is that there are at least three important questions to develop one RDMFT. So I would say that the first one is, of course, the functional. We can find some exact condition for the functional. The functional is in general or should be functional of the one body density matrix, and we can find some exact functional, but for very reduced systems. And in general, we will need some approximation, and this is a difficult work. Second question is where we're going to optimize or to do the minimization, and this is the question about the domain. So here is an example of the domain of the bosonic functionals, but also the description of this domain is not trivial. So I think it's also an important question. But I think a third question is how we are going to make the optimization. And I think this is a question that we sometimes overlooked because this method, the 1RDM, should be at least more economical than wave function methods. And I think this question about how quick, how economical, or how we are going to perform this kind of minimization is an important question of the whole project of 1RDMFT. Of course, one of the competitor is DFT, and when DFT works very well, I think there is no too much room for 1RDM FT, but in general, for strong correlation systems, there will be a lot of room provided that we can do these minimizations effectively. So one candidate is, of course, use machine learning techniques. Someone, I don't remember, maybe it was Jerzy or Christian, say that maybe if we can keep all the information of all the ground state solutions that we perform daily in this planet, and we keep the information of the energy and the one body density matrix in a data set, so that would be the perfect setting to do machine learning, because then we can fit and find the universal functional using all these data. Of course, this is a kind of utopia, because to keep this information is also another difficult task. But there is a subfield in DFT, which is actually trying to learn the universal functional of DFT using machine learning. This is not as developed as material science, that you have big data from DFT calculation of the energy or gaps, etc. And then you can train a neural network with real observables. Here, the question is different, is how to do machine learning for DFT. So there are essentially two ways. So historically, there are two ways to do this kind of approximation for DFT. One is to learn directly the Hohenberg-Kohn map here, which given an external potential, learn the density, the energy. And this is, of course, very legitimate question. And I think this is historically how the first attempts to do machine learning DFT were done. But the second is to use the structure of the Kohn-Sham equations. And here we have a second question, is what is the exchange correlation potential? So this is the Hartree-Fock or Kohn-Sham equations with external potential, which is given for the external potential properly, Hartree potential and the external potential, exchange correlation potential. And this exchange correlation potential, as you know, is given by the functional derivative of the density of the functional derivative of the exchange correlation functional in terms of the density. So these three ingredients at least will give you a solution of the Kohn-Sham problem. We use with the exchange correlation potential and with the exchange correlation functional. So this is our second way to do machine learning in DFT, is to learn the potential and this functional. So this is just a quick summary. The idea of learning this kind of functional is especially in the regime of strong non-local correlation, so non-local functional. So the whole non-locality of the functional can be, in principle, be learned by machine learning. Also, learn this exchange correlation potential and learning non-interacting kinetic energy functional. Also, there are attempts to do it. But in general, the input will be the density and the output will be, in principle, the exchange correlation functional with some conditions. So one of the things, the first thing we did in machine learning for DFT was with this philosophy, so starting with some density here, learn the exchange correlation functional, but using some techniques that basically any toolbox of machine learning has right now, which is differentiation, we can also train the exact functional derivative of the functional, which is the exchange correlation potential. So if you produce some data from some particular system with exact densities, exact functional exchange correlation energy, and the exact exchange correlation potential, you can train all these variables, right? And this is exactly what we did. But there is another advantage of doing this kind of trainings is that you can choose the information of the density you want to enter into the neural network. So for instance, we solved a 1D system in a grid, and then the profile of the density is taking values of that grid. But you can take 1 point of the density at each position. You can take 2 points of the density in each position, neighborhoods, or you can take 3, 4, etc. So by taking this, you can make a concrete resemblance or a direct resemblance of the hierarchy of functional in DFT. So here, if you take 1 point of the density, it will be like a neural network LDA. If you take 2 points, it will be like neural network GGA, and so on and so forth. So you can take actually as many points as you want. And this is the information that is going to the neural network. So we train in Octopus, we obtain exact data for 2 electrons in the random potential with 2 nuclei. Everything interacts with 1D Coulomb interaction. And then we make, by solving this problem, so it is a electronic system, but we put the spin, the singlet in the spin part. So essentially you can think that it's actually a 1 electron problem with 2 coordinates, right? And it's possible to solve it. And then we can obtain the exact values for the exchange correlation for energy and the exact value for the exchange correlation potential. So this is the kind of information that enter into the neural network. Here is 1 density, and here is the corresponding external potential of that density. And from there, we produce also the exchange correlation potential and the exchange correlation energy. So the loss function we use, and I think at this year was also, okay, this work was 3 years ago, so maybe right now is a little bit obvious that one can do this, but at that time was not so obvious. So we trained the exchange correlation function, energy here, but also the exchange correlation potential as the exact functional derivative of the exchange correlation function. And then we also trained the derivative for stability, the derivative of the exchange correlation potential, and so on. And then we can produce all the framework of the constant system and compute energies in a constant framework. The only difference is that we don't have explicit expression for the exchange correlation potential of the exchange correlation energy, but we have a neural network that provides this data. So here is the solution of the H2 in the dissociation. Here is in yellow is a neural network trained with 1 point data, so neural network LDA. In blue is the real LDA. So our LDA is worse than real LDA. But then we started to put more non-locality in the training. So for instance, here we have 15 points. So imagine a kind of information that much more developed GGA. And finally, something like 30 points, we obtain essentially the exact curve using constant system. Here I have to say that we train the systems we are taking here is 201 points, 201 grid points. So of course, this degree of locality will be related with the system we are taking. So for instance, if you take a lot of points, 100 points, you overfit, and the system is not so good anymore. Okay. We also we did the homogeneous electron gas in this proposal, but essentially this paper was to propose the idea that training the exact derivative functional of the exchange correlation functional, like the exchange correlation potential, it makes sense, but to improve machine learning for TFT. But of course, this is a part of a big project. Several groups are involved. But so far, there was the state of the art is let's say October of last year when we did this second work. All machine learning functionals are essentially trained with integer, or mainly with an integer number of electrons. So this is good because you can obtain some data for this kind of systems, but you know that there are important constraints in the exact function of DFT that contains a lot of physical information. And in particular, it is the very famous derivative discontinuity of the exchange correlation function. And with this derivative discontinuity, you can compute electronic band gaps or change transfer excitations, just to mention two kind of things that you can compute with this derivative discontinuity. So it is a kind of ensemble DFT, I think, is just to make the superposition of n particles and n+1 particles at the level of the density. And also here, the energy will be a superposition of the energy of n particles and the energy of n-1 particles. And from here, you can construct the exchange correlation potential, the exchange correlation function. So again, we did the same procedure. We use 1D systems. This is done in Octopus, and we perform the calculation for 1 electron, 2 electrons, and 3 electrons, right? And the background of this is 1 positive charge randomly put in the lattice, 2 positive charge randomly put in the lattice, and 3 positive charge randomly put in the lattice. And with this, we have essentially neutral systems with different number of particles. And from here, we have extension of what I presented before to an integer number of, a non-integer number of particles. So the training is essentially the same as before, but there is a second neural network here that was specifically introduced to account for the derivative discontinuity of the exchange correlation function. So we put the training, so here we have to train a function. It's not important here, all the training parameters are here, but the essential point is that we put a specific function which is derivative discontinuous at integer number of particles. So of course it could be artificial in the sense that we force the neural network to learn that, but I will show you that with only this change in the structure of the architecture of the neural network, we are able to reproduce, for instance, the jump of the exchange correlation potential when you cross an integer number of particles. So here is the example. Here is one of those of the systems that we train. And here is the energy. This is the energy when the system goes from 1, 2 to 3 particles by changing the parameter, right? So the exact energy is here is flat, and here there is derivative discontinuity, and here is also flat. And there are 2 models here. The first model A, we train only with fixed number of particles without introducing this derivative discontinuity or this sinus in the architecture. And then what is clear, it is enabled to reproduce the correct behavior of the energy. The second model is we introduce that architecture and we obtain exactly the correct expression for the energy. And here you can compare the errors. Also, this a little bit more serious the problem, because without considering the exact behavior, this error is completely random here. So it is sometimes it's above, sometimes it's below the correct energy. And here it is now the prediction of the neural network. So here we have the model A, so without the specific imposing of the derivative discontinuity. And here is a system. So here you can see 2 systems. This is one system is with 2 electrons, and the other one is with 2.01 electrons. And you can see the exchange correlation potential. Here is the model A without that architecture, and here there is no jump. So essentially the exchange correlation potential for 2 electrons and for 2.01 electrons is essentially the same. But here you can see clearly a jump of the exchange correlation potential when you cross the integer number of particles. So in this whole architecture, you can see that it is at least able at this level of the 1D systems to reproduce all these exact conditions in this case. And here, using the conscience system, we compute the energy of helium. So here is 1 electron in helium, 2 electrons in helium, 3 electrons in helium. In black is the exact energy, and here is the prediction of the machine learning architecture I presented before. So here it is really good the fit, and here is essentially bad. The reason for this error here in the prediction of the energy is that when we trained the neural network was only allowed to see densities that come from neutral systems. So you can see a general feature of neural networks of machine learning is that extrapolation in general doesn't work. So the interpolation is really good, but extrapolation here doesn't work like we expected. So, but the solution in general of this kind of problems should be easy. You only allowed, and you have only allowed the neural network to see densities that comes from systems without neutral charge. So with all these ideas in mind, so I present my first attempt to do a machine learning for reduced density matrix functional theory. So I started with the Bose-Hubbard Hamiltonian. And here you can see, and it's translation invariant, so there is no external potential. And then if you identify this in the constraint search approach to solve this in the context of one RDM, you need only two parameters. One is the filling here, so the expected value of each site. And second, the only need is this guy here, which is the expected value of the non-diagonal terms that appear here in the Hamiltonian, right? All these, all the rest of the one body density matrix. So for instance, the expected value of j plus 2 or j plus 3, etc. You can put it in the whole minimization procedure. So at the end, the universal functional unit will be a function of only these two parameters. And here you can see for 2 sites, 4 sites, 6 sites, the universal functional is a function of eta, this parameter, and here is filling 1 and filling 2. So this is a general feature of all these functionals that go in with this convexity. And here you can see the Bose-Einstein force. So here you can see that the derivative here is always diverge, right? So what we did here was first, we took a very simple system, the Bose-Hubbard dimer, for which we know the exact solutions, and we put it in a neural network. So here we only put eta, this value that classify in reality the wave function, the one body density matrix, and we put US. U is the unitary transformation that diagonalize the one body density matrix, and S is the occupation numbers, just to put more data. And then we put N, the number of particles, and M, the number of sites. So in this case, for this example, I am putting just 2 and 2. And I trained a fully connected neural network, exactly like we did for DFT, and produced a functional. The functional essentially here is exact because we have exceptionally good data, have exact data for this functional. But I want to show you here is that this guy, so this neural network also learns the derivative. And I think the derivative of this functional is a very important concept that you should consider in the development of one RDMFT, because it's derivative that would allow us to perform the minimization of the functional and the one body energy. And you can see that, okay, here it is essentially exact this calculation. And you can see also the Bose-Einstein force here. And what we also realize is that for larger systems, to train when you are close to the Bose-Einstein condensation point is more difficult. And it's more difficult because these points are going to be very separated as a consequence of the Bose-Einstein force. So the second thing is, if we want to go to larger systems, let's say 40 bosons in 40 sites or more, the Hilbert space is huge. Here, this Hilbert space is of the order of 10 to 22. So we can forget from the very beginning Levy search constraints, at least like all wave functions given a corresponding one body density matrix. But we discovered we facilitate our lives by making the following observation. If you observe the one body density matrix here, this is of course expected value for a given one wave function of creation annihilation operator. And you can think that this is a wave function with n-1 particles, right? And then you can write this in the Hilbert space of n-1 particles. And then you can produce a set of wave functions with n-1 particles. And the angles of all wave functions are related with the entries of the one body density matrix. So this is very interesting because if you do the Schmidt decomposition of this coefficient here, You can then, for this kind of relational invariant systems, you can prove that the minimization goes only in the set of orthogonal matrices M times M, which is the dimension of this B here. So by doing this minimization here, the minimization is performed in the following place. Imagine that you solve the problem and you obtain the ground state. And then from this ground state, you obtain the one body density matrix. This M with N minus one particles define a subspace in the Hilbert space. If you allow to rotate all this in this subspace, the minimum will be always attached in the correct one body density matrix. So this is explanation of this minimization here. And then the only thing you have to do is to perform the minimization in the set of orthogonal matrices. So this minimization or this search constraint here is essentially exact until 20 bosons and 20 sites. And here is where we started to see the deviation. So the procedure is not exact, so we have to work more. But here you are seeing the results of 40 sites and 40 bosons. And we are comparing with quantum Monte Carlo, which is essentially exact for those systems. So here, for the so-called strong correlation regime, the results are essentially exact. In this weakly correlation regime is exact. And in the intermediate regime, which is the challenging regime for those systems, because the coefficient or the kinetic energy as of the same weight of the interaction energy is challenging. But here I also plot here the functional of this. And what I see is that, so this is the functional and this is the total energy of the system. And the interesting point for me is that at least for this invariant system, this relational invariant system, we can solve this problem in the context of one RDM with only two parameters, filling and the first non-diagonal terms that are actually the same. So this problem in the context of one RDM is effectively with only one parameter, what I think is quite remarkable. So as an outlook of this work, I really think that we should consider machine learning as a way to produce universal functionals, not only for the case of bosons, but also obviously for the case of fermions. And I also think that in general, this could be a tool that can help us to develop functionals, or at least to perform the minimizations in general when we have good or approximate functionals. And with this, I conclude my presentation, and I thank you for your attention.